And yeah, let's get started. So the idea for this video recording is I've recently completed the development of MLOps materials that I want to present. Um, so since it's all kind of still fresh in my mind, and before moving to other topics, I just want to capture the this video recording mostly uh, for future reference, so to speak. So here we'll be discussing MLOps, what it looks like today in mid 2026. So we're going to be covering 6 modules. Just like and yeah, with that, let's just go ahead and get started. So it's mostly going to be a theoretical high-level walkthrough. With and for the practical and it's going to have a practical component as well. We won't get into a demo. We'll just kind of show like a screenshot or something and give a brief commentary on what that may look like. So let's get started on module 1. We'll cover the foundations of machine learning lifecycle. All right. For this module, we'll be covering these 4 topics. What the end-to-end looks like, and then like how do we start defining the infrastructure, what defining success metrics, and then a practical walkthrough if we just to kind of give the idea. So first, the 5-stage blueprint. So most machine learning, AI, LLM, traditional ML lifecycle looks something like this. It doesn't mean like that every project needs to start from the very beginning and then sort of iterate, right? So, but in a broad sense, if you're training a model from scratch from the very beginning, you may start like first of all, you need to define your key performance your problem definition. You need to define what the problem is that you're trying to solve. So it can be something like a computer vision project, maybe detecting some. There's something we're working on recently to detect some quality control for computer vision, maybe to detect some um, pills or some manufacturing defects with computer vision. It could be like a chatbot, etc. There are many different use cases. The important thing here is going to be to identify how are you going to define key performance indicators for the problem definitions. So a KPI is how you're going to measure success. So for example, for the quality performance, quality control use case, maybe you can say, oh, we're reducing batch errors, or we're detecting them more often than you would with a human eyesight, and it's costing us less to do so. So things like that, and you have to actually once you finish like the whole life cycle, you actually have to demonstrate that you're surpassing whatever KPI you've set up. So after you kind of set the problem definition and how you're going to measure success, you start to define, okay, they're different. If you're going to do end-to-end, you might want to gather the data. What are your data sources that you're going to be using? What are the algorithms? How are you going to train? Um, Nowadays, you don't really focus on training as much. Like a traditional I'd say organization may train some traditional machine learning, like an XGBoost algorithm or some simple tabular data or a simple computer vision data. But usually, whenever you're dealing with large language models, it might not be every organization that's going to be training. It's probably going to be a small subset of organizations that are training these large foundation models. Um, so it's more going to be like we're going to be fine tuning, but we'll get into these details later on. Um, so that'd be kind of like how we're adjusting the weights of our model, right? Then how are we going to deploy the model? So this typically encompasses, okay, what's the endpoint going to look like? How are requests going to be hitting our endpoint, and how are we going to generate those predictions, so to speak? And it's yeah, we'll be covering this in a future slide in detail. Then, okay, how do we integrate applications? So right here, this is more geared toward like the agentic era that we're seeing right now. So an agent is a typical application that's interacting with your model somehow and obtaining useful prompt responses, so to speak. So that'd be an example of an application integration, a common one seen today. Another example for the quality control one would be, let's say you're taking you're currently in a manufacturing site and you're taking a bunch of photographs of your a sample of your uh, batch product, so to speak, and you send those to your endpoint, and then you get a result. Okay, maybe there's a defect or it's all good. So things like that. That would be the application layer, how it integrates. And then this is an important one as well. How do we like the observability layer, which is how we collect all that telemetry data. We'll get into the details, but telemetry means telemetry from our underlying infrastructure that are probably training or serving the models. Maybe how is our GPU memory? How are our resources performing? And also like some more model behavioral data you can capture, like you can capture some prompt spans, which we'll see later on in the modern era, some accuracy metrics, how are we tracking our model evaluation, things like that. And the flywheel, which is, okay, how do we perform actionable, how do we modify our system, our end-to-end system, so that we improve every time, right? So how do we use our observed data, right, to improve the system, so to speak? And here, recall we were talking about KPIs. Here, okay, it's an important aspect. How are we measuring our success? Are we getting closer? Are we getting further away? Maybe it's costing us more money to implement the system than what we had before. So that's important considerations that you need to have. Okay, at a high level, you'll get these. So just taking a step back. Once you deploy a model, you have a model deployed in production, you need to consider three things. One is like the physical resources. Are we using, like, what does the disk look like, the network? Are we on GPU, CPU? What are our like RAM, just regular RAM, or our video RAM for the GPUs? Um, what does our control plane look like? So usually you won't only be serving like one model. Um, you you uh, you might be serving a mesh, or this might be running under like a network mesh or some form of control plane. So that'd be like a network, sort of network layer right here. And the top one is like an AI gateway. This is mostly currently deployed as a proxy layer that helps you capture all the telemetry data, so to speak, which we'll get into later on. So first, scoping and constraints. One of the important things here is so the data in traditional machine learning. If you're going to be training from the ground up, you need to identify, okay, do we have the data? What's the data we're going to be using? And if you're training, from scratch, you probably need to do a bunch of data engineering to, like, I don't know, de-identify data or whatnot, right? So you need to think about what that looks like. Another thing to consider is, like, are we going to be using our own models? Are we going to be downloading some open weights models? So all those considerations you need to keep in mind. So another one is yeah, like the hardware, right? So typically every time, and this is more true right now, whenever you're thinking about deploying an open source model, you need to kind of make sure that you have enough compute budget to service the model, especially under high concurrency, as we'll see later on. All right. So I guess another important one is, are you going to be using your own models, or like open source models, commercial models like the Claude, Gemini, Open AI, things like that? So we'll probably cover this in in a future slide as well. Um, but you need to also consider what data are you sending up to those models, because yeah, your enterprise might have a boundary on what data you want to share or not, right? So just things to consider. Let's continue. So what does success look like for a model, so to speak? So some of the metrics you want to capture is time to first token. Like that means how long does a request take to be serviced, so to speak. So if your request takes, I don't know, like 20 seconds, it's potentially going to be a lower, but it doesn't, it depends on the use case, but that's something that we definitely capture to measure, like what's the latency of our model, how efficiently are we handling those requests. And this is going to be true, like for example, if we want to handle 20 concurrent users in our model, it's definitely a metric we want to capture. The same as key value cache saturation. So the key value caches generally stores our context windows for each of the users. They're nowadays there's some things like batching going on, but it's also a metric we want to capture, and we'll show uh, we'll show a dashboard later on capturing all of these metrics. All right, so GPU VRAM profiling. Uh, so here, I guess what this slide captures is whenever you're thinking of deploying a model, and let's just say like a large language model, you need to keep into consideration what's your VRAM real estate. How much VRAM do you have available? And then let's say like if we take an H100 GPU, which has 80 gigabytes of RAM. This so you've already considered, okay, that's our physical resources to sort of serve a model, right? So here we categorize this into both serving a model or training a model. So you need to plan in advance, like how you're going to be filling up that RAM, the video RAM, for GPUs here. I mean, yeah, for GPU devices. So whenever you're deploying a model, for example, if you're deploying you need to go look at the documentation of the model. Like suppose you're deploying like an open source model, and you just want to deploy it for inference. You're typically not going to train a very large language model, so to speak. In most cases, you can do, depends on your organization, but Um, if you're just going to deploy a model, you might kind of say, okay, go into Hugging Face, maybe look at the Qwen documentation or DeepSeek documentation, an open source model. And so you might want to plan, okay, what's my available GPU? How much is going to be spent on weights? So like you can say 30% is going to be just the model itself to load its weights onto that GPU RAM. You should consider, for the dense architectures, you should consider storing 65% for key value cache. So that's a lot of key value cache, and just plan a little bit of overhead there. So if your model, you might need to do some calculations to see, okay, how many parameters is our model? How many floating? What's the precision or the quantization of the model, and then will that fit into our GPU? Now, there are different deployment paradigms I think we'll cover in a future slide. Like it doesn't have to be a single GPU. It can also be a multi-GPU environment. But for now, let's just keep it as total RAM, right? Uh, Now, if you're deploying a sparse mixture of experts model, you may notice how this is mostly allocated toward weights and just a little bit of KV cache. So that's typically the way that MOE architecture works, it only holds I mean, you can go read more about like a Dance LLM and MOE LLM online. But long story short, MOE kind of was created to solve the key value bottleneck. So what this does is it effectively uses just a small portion of the weights, and it has more efficient lower KV cache requirements. But yeah, you can definitely go and see online like what are the architectural changes that enable this. One of the drawbacks here is that you might have a bunch of weights loaded that you will not be using or will not get activated at any given time. But there are some, these are some of the trade-offs that you might need to consider when planning. And if you're going to be fine-tuning, like yeah, this is a common if you're going to be loading like a large language model, not pre-training from scratch, so to speak, but you're going to be fine-tuning it. So it's sort of a hybrid here. So you're still going to have your weights. You're going to be fine-tuning a little bit, not a lot. You're not going to be training from scratch, so to speak, but you will need a little bit of provisioning for that. And yeah, it'll definitely be something much lighter weight. But okay, let's just move on. Hopefully this slide is self-explanatory. This is an example of a dashboard, a live dashboard of things you can track. Like once you've deployed, in this case, we're showcasing a Qwen 3 open weights model thinking. So you can show things like the time to first token, latency that takes for like a request to come in and resolve the first token. Things like that. So this is like a dashboard, VLLM dashboard you can download from Grafana, open source. And yeah, you can just showcase a bunch. This is part of like the observability, and it's definitely helpful to kind of see what's going on, right? I think one of these panes right here was a key value cache. I think we'll get into it later on, but yeah. Okay, let's just go ahead and continue. All right, so that was module 1. Now we're going to go into module 2. We'll be covering these topics: governance, data orchestration, data processing and querying. So this is going to be sort of like for a training paradigm. But yeah, let's just go. So yeah, if you're going to be like training or fine tuning, usually for governance you have to capture 3 things. One is you need to tie your Git commit, and this is mostly for governance, right? So you need to tie your Git commit, like whenever you submit a Git and then publish a release, etc. You get a hash code. So that hash code is the code you're going to be running. It's your immutable code. So you need to tie that with a Docker. So generally you'll create some, or not Docker, like a container, Open Container Initiative Digest. So you generally also keep a immutable container registry. And what's your data snapshot? The data snapshot you use for training the model, right? So you'll typically need to store these 3 things for every model version you develop. So let's say you develop model version 0.01. You capture all of these and then store those like for governance into some bucket. Then once version 2 comes up, maybe you've deployed the model, captured some observability data, some behavioral data, and you decide you want to upload your update like the flywheel of your deployed model. You want to maybe perform some optimization for token optimization, right? So you'll want to capture these 3 things. What's the data you used? What's your container that you currently deployed, and what's the actual code for that? So some of the things that you'll be tracking whenever you're deploying a model, and just going through the whole MLOps lifecycle in general. We already talked about some of the things that we'll be capturing, like whatever code got committed, the data that you trained, the container that's actually getting deployed. Other things that you'll be monitoring from the like runtime metrics, which we already showcased, like, okay, what's our GPU usage, our time to first token. So these are going to be for like quality control metrics that you'll be gathering. So what's the model checkpoints for the model version? All of this is going to live in some object store. Maybe you're going to be capturing some prompts also for like quality control or improving some aspects of the model interaction. And hyperparameters, so things like what is the configuration for the model that you're currently using? Yeah, all of that you store and you track it, and you kind of just monitor it for overall governance. The idea here is that, like, if you need to roll back a model or go back to like a specific point in time and kind of see what happened here, you should have a specific record of like all of the data that we use, the code and everything. You should be able to go back in time and kind of open that snapshot up and see what potentially caused an issue or things like that. Or maybe if you need to perform a rollback to some version, etc. Okay, so now let's go to distributed data orchestration and caching. All right, so what we're showing here is what you'll typically see in a complex, I'd say, training or fine-tuning workload, right? So suppose, yeah, so here a training or fine-tuning pipeline. It's gonna look something like this. So the underlying infrastructure might be like a Kubernetes. The Kubeflow is just like the graph, the execution graph, or the workflow. So workflow might look something like this. So it might first go and fetch what's the data version we need? What are our data sets? It's gonna want to fetch that. Like, okay, what's our delta data that we're gonna train on or fine tune on, or our historical data? I don't know. So it's gonna get all that data from here, from an actual storage platform. It might be like in a colder tier. So what's going to happen here is you're going to have some Iceberg is like for structured data or maybe like images in an unstructured data, and you're going to want to first of all identify, okay, what's our data going to be? We're going to want to bring them closer to the compute, right? So that our process doesn't have to go back and forth all the time whenever it's training. You need to start to bring it closer to the compute, like into a cache layer. So these are just some logos that I've put in here that may be useful to look into for table caching, and by caching I mean like disk. It's a disk cache here, right? So Fluid is like a locality awareness system on Kubernetes, and both of these are like um, for local, what we call it disk cache, but it's really just like yeah, like making just making it aware, making your processes aware of where the data is. So something like a yarn, if you're familiar with like yet another resource negotiator. But this is for like Kubernetes, so to speak, for tables and for objects. So it's important to kind of bring the data as close as you can as possible. So for example, if you're going to be using RAID data or Presto, you can also cache in memory. So bringing it even closer to the compute. So we have Feast and MLflow here. This is for like metadata tracking. Just to kind of know, okay, what's our data version that we're going to be using for this particular fine-tuning run or training run. So once you get all that data in place, you bring it like to a local disk, and then you bring it to your memory cache. Once it's close enough, then you can start sort of your training or fine-tuning job. So what you'll typically see in a distributed environment is going to be like a RAID cluster, and maybe running a bunch of worker executions, a bunch of workers, and that's going to be like a distributed fine-tuning or training. Some of the tools that you might see, JAX, PyTorch, or RLib for reinforcement learning. Yep. So once they're trained, it's going to go through. We're going to, of course, store the files, which we'll see in a later slide. But it's going to go through some post-validation evaluation, and then like as a last step here, we're going to sort of generate the model card. So you may know this applies for like fine-tuning or even like a very large language model training. It might look something like this, just probably a little more complex. But yes, you'll generate the model card, which kind of just describes whatever this model is. And you generate a tag as we defined earlier. Maybe it's model version 0.2 now. And we promote it to staging, and maybe send some notification. Or for the tags, maybe we want to register this, like what the data is, what the container for the training, what the actual, so what the pod code looks like. So we're gonna keep all this lineage as we spoke about earlier. So once this model is ready, we'll probably in a future section we'll see like what the deployment looks like. But for now, let's just kind of keep it here. So we already said. So the data processing is going to be very important here. How it gets from here all the way to the hot tier, so to speak, from cold to hot tier. So yeah, I think we already described it, so I'm just going to go ahead and skip this. But yeah, let's just skip for now. That's an example of MLflow dashboard. So you'll see like every experiment or every run. So you can report things like your accuracy or things like that. I mean, if you amplify this, you can also add some tags of every run. But MLflow is going to be a good tool for tracking all the metadata associated to your training. Yeah. Okay, let's continue. So you might notice also like the trained data sets, the hash codes here, the accuracy that this provided, and other things. All right, so this is just like a statistic. Like if you were to reach out directly to your S3 during training time, or yeah, during training time, like it's just going to be slower, right? So it's a good idea to take advantage of some caching mechanism. Okay, so now on to module 3. I think we already covered this section. So for example, yeah, we already covered like how a distributed training may look like, the underlying infrastructure. So we mentioned like, okay, you may have a kubeRAI and that's sort of hosting a PyTorch and JAX libraries across multiple pods or nodes, so to speak. Now we're gonna specifically focus on like the parallel training portion of it. So there are two model parallelism strategies. One is the single node multi-GPU, and then there's the internode. So it's going to be like the multi-node multi-GPU. So I think the important thing to consider here is FSDP, and tensor parallel. So whenever you're training, the weights are going to be distributed across multiple GPUs. So like a single forward backward pass, it needs to go and touch each of those GPUs wherever the model weights are hosted. So you need to have extremely fast communication between both of these. I mean, not both, between all the GPUs devices that are connected to produce a very large language model. So yeah, just make sure, depending on what you're using, just you'll probably need to make sure you have the bandwidth to um, yeah, to support those operations. And the same is true for the serving side. So sometimes, if you're serving like a very like a 1.5 trillion parameter um, model, it doesn't fit into a single GPU. So yeah, you need to take these things into consideration. It also depends on the architecture and whatnot, but yeah. Uh, Parameter efficient fine tuning. So what's done commonly, like in organizations that don't necessarily need to train these like full training, so to speak. You can do something called fine tuning. So fine tuning means taking a base like a base model and updating its weights. So maybe we downloaded some model from Hugging Face and we just want to fine tune it to our with some additional data, proprietary data maybe. Um, so you can do two things here. And we're not covering like the full training from scratch, right? Maybe we just take a model that already has all that English encoded into it or language encoded into it, math skills, etc. Whoever published the original model that was a fully pre-trained model. So here we're just kind of adjusting the weights, so to speak. Maybe what you need to do is some domain adaptation on the model. To give an example, maybe you have a model and you have a bunch of agents hitting that specific model. And you maybe want the model to kind of learn how to give more concise or better structured JSON or tabular CSV data with much lower token utilization or not as verbose output, so to speak. You can fine tune the behavior of the model, so that like this, yeah, the model behavior or styles a little bit. So you can guide it towards specific domain adaptation and that's called parameter efficient fine tuning, where instead of fine tuning all the billions of parameters, you maybe just update or inject a few additional weights here and there in the model and you just fine tune it, you just fine tune those specific weights. So it's probably going to be like a point, not even like a 1% of the models, maybe. I think okay. Another thing also like to know here is that whenever you're serving a model, you can also serve a bunch of this. Let's say you serve your frozen weights model. I mean, I don't know that we'll get enough time to get into the details, but let's say your 32 billion parameter original model is you consider that as a frozen weights model. And on top of that frozen weights model, you're going to have a bunch of different adapters. So those are called LoRa adapters, low rank adaptation. So you might have one adapter that's specifically fine-tuned for producing that output, like the JSON output or efficient CSV output. You might have a different adapter that's specializing in low verbosity output, etc. So yeah, so these are very small footprint compared to the frozen weights, so you can deploy a bunch of them on top of your yeah, you can deploy a bunch of them. Okay, so a similar thing happens here with where you can sort of fine tune in this case it's an adaptation that you perform on the deployed model, but in this case it's more for reasoning alignment for like the thinking component. So a few things here are the verifiable rewards or GRPO or PPO. So so it's a similar concept to the PEFT LoRa adapters, but this is more for like the thought thought the thought sequences and the reasoning portion of the models, thinking models. All right, so some evaluations. So here, I guess we'll cover like how do you evaluate if a model is being let's say if it's being useful or not. So there's this concept known as LLM as a judge scoring. So what this is so for example, you can define a key metric. To give an example, maybe usefulness. So you're gonna generate a data set of prompts with I mean you can use an LLM for this, but you can generate 100 prompts, right? With some LLM or whatnot. And then you're going to have your model under evaluation. And what's going to happen is, so you're going to submit all these 100 prompts to your model and then just generate the responses back, right? And then you're going to have an extra, that's where like an extra LLM comes in, and that's called LLM as a judge, which is pretty much going to evaluate the usefulness of the response or um, in this case, we defined usefulness as an objective function, but it could be any other objective function, right? So that's what LLM as a judge is, and it's used basically like for pre-deploy evaluation of a model. So some quality control there. Yeah. So if it fails these evaluations that you may have, you can just not deploy it and kind of yeah, you need to do some additional fine tuning or something like that. All right, this is just what quantization is. So here we just want to say like whenever you deploy a model for inference, um, you may want to we covered earlier like how much gigabyte of VRAM it's gonna use up. So that's gonna sort of impact um, your performance in terms of like the maybe like user evaluation scores, maybe low. We're getting low time to first token or something like that. Um, so here, a technique that's commonly employed is something called quantization, and this simply means so let's say like model weights are currently stored as floating point 16 bits. You can just say, oh, well, this is something that's designed from training time, but I guess whenever you deploy a model, you can specify a configuration that says deploy it as floating point 4 bits. So it's going to be, of course, 1/4 of the model size. So it's going to fit in your RAM. It's probably going to still maintain those like the model intelligence, so to speak. But it may also be the case that there are some like encoded knowledge into the model that gets lost. So there are some specific metrics to evaluate, like how like what sort of model connections you lost or knowledge encodings that are no longer functioning as expected. So yeah, the like whenever you quantize, want to deploy a quantized model, you could look if and see if there are any benchmarks. Um, yeah, so yeah, there are different right now some different techniques to on during training time to sort of ensure that that there's not much how do you how to say this like that you don't lose as much predictive accuracy or correctness of a quantized model. But that's what a quantized model is pretty much. So it's just 1/4 of the resources required. So it may fit into a single GPU or even like a local client or something like that. Um, all right, so evaluation metrics. We talked about this earlier, like during the LLM as a judge. So you might have different objective functions or evaluation metrics. So you might want to say answer relevance, maybe. So yeah, these are some you might want to, like, whenever you're thinking about how to evaluate a model, you probably you need to generate, like, how are we going to evaluate this model, like the behavioral aspects of it, or something, or yeah, like, or something else, right, like the time to first token, etc. But this is more like around the behavioral aspects of a model, like, how is it answering relevantly, etc. Um, and that's how you'll decide if you actually promote a model up to like a staging, or a potential model candidate up to like a staging environment, or if you need to go back and rework it. So that's the main idea here. And we kind of covered this in LLM as a judge. Okay, now we're gonna dive into the inference architecture. All right, so for inference, what I've done is I've kind of, and this was very confusing for me, kind of getting up to when I was getting up to speed with all of this, and like throughout the past 2 years. So I decided to just kind of create a table and hopefully clarify things. And especially because things have moved very rapidly from like 2024 to today, with all this LLM revolution, etc. So let's just go. This section is going to be around model deployment. So inference time. Um, so I've divided this into like 7 layers, and yeah. So let's start here. So there's 7 layers that will be considered. Here we're going to be looking at again as in the context of like the inference side of the house. So you'll start with probably like a model weights already pre-trained. It could be like a model weights, or um, and your LoRa weights, right? So these are some of the formats that you might see. Um, yeah. So if it's a large language model, that's what encodes the weights right here. So pretty much, yeah. Okay, let's just continue. That's just a model on disk. Then what happens is layer 2 is like a compiler that takes that model and then uh, um, compiles it into an execution, execution. Okay, yeah. So here, if you're familiar with Torch, you're familiar with Torch compile, TensorRT, or Apache TVM. This is one you'll see for smaller footprint. I mean, I've seen this one mostly like in smaller footprint, like TinyML type of environments, IoT, things like that. But you'll compile this into like the computational graph. Then once you compile it, you kind of you need to deploy to like an inference engine. So here, yeah, like some common engines seen today are VLLM. That's pretty like the workhorse right now, and the core, VLLM core. So there are 2 parts of VLLM. I'll cover them right here, but VLLM core is mostly like how the scheduling happens between the physical GPU execution and like the and the serving layer. So okay, so VLLM core is that like the page detention mechanism for efficient key value cache. But another common one is like TensorRT LLM, SGLang, and yeah, Triton, or yeah, okay, OpenVINO. These are things you'll see here. This mostly has to do with like scheduling resources on the actual physical like GPUs, so to speak. And then there's going to be like an entry point, like a serving layer. So there's going to be like a HTTP, REST, gRPC. So for example, whenever we see VLLM, it's actually two components. It's like the serving layer, like the endpoint, and then the actual physical execution and scheduling, etc., which is like the memory management and all of that is the VLLM core, right? So things you'll see here in the serving layer, level 4, Triton IS, VLLM, the Fast API, which is Fast API. Whoops, Fast API, and TGI router, things like that. All right, so maybe going a higher level up, this is more about packaging. So whenever you see like NVIDIA NIM, and it's like a custom Docker container, it's like more around how you package like the model and the serving and the runtime, etc. And then higher up is the control plane. So control plane, you'll see things like Kserve, which is like the orchestration, Rayserve as well. So it kind of it can distribute. So for Kserve, you can manage things like a canary rollout between model A, model B, or rollbacks. So things of this nature. Istio is going to be like the microservices mesh network. Maybe you can have some network policies in there about traffic routing, etc. Network traffic routing. And Rayserve, this is going to be pretty much the very common in if you're going to be deploying like cross like multi GPU, multi-node models, you might see like a Rayserve in there. There's also some mechanisms. I think we'll see this later on, but yeah, this is going to be mainly for the control plane. And higher up for like an AI gateway, this is going to be more around it's going to be like a proxy layer. So every request that wants to come into like into our we might not only be serving one model, we might be serving a bunch of different models. So we want to have that observability layer, so or gateway, AI gateway. So Kserve might be or Rayserve may be orchestrating all of these models. Light LLM is more like just a proxy, so it's gonna allow things like to capture some telemetry data maybe, or the latency, like logs, spans, etc. I think we'll be covering this in the observability layer later on, and that's AI Gateway. So hopefully that clears up a few things about how like yeah how model inference works in general. Yeah, let's move on. So yeah, I think we so we already covered sort of like VLLM page attention, which is the runtime engine that's commonly deployed right here, VLLM. And it's useful because it solved a key value cache problem that we had. So it you can read more about this online, but it's the main workhorse right now for LLMs for a reason, and that reason is that there used to be like a big bottleneck on key value cache utilization, and this page attention sort of helps manage this. So yeah, there's plenty of resources online, and that's definitely one of the things you might want to consider, like what your runtime is, but it's most likely, yeah, that's just what we wanted to express here. Okay, so some optimization things. So whenever you're serving a model, there's something called prefix caching, which just says like, so instead of having to load all the weights every time like a new request comes in, you can cache, you can pre-cache your KV cache. Sorry, you can cache your KV cache. So yeah, that's called prefix caching. So it doesn't have to load everything from it doesn't have to load the whole context window, so to speak, into the V video RAM. it can just perform a simple lookup operation on some prefix cache and serve that in a much faster way. So that's prefix caching. It's generally going to be an argument you pass to your whenever you're deploying a model. You can say, "Oh, I want you to do prefix caching," and it'll provide. It has this mechanism in place. Um, so yeah, it's generally a good idea to have that there. Mm, all right. So yeah, as this okay, and so yeah. Now let's. I think these were what the layers 1 through 3 is pretty much this. The engine, the runtime, some ideas here to kind of optimize it. Um, Now, what does the 4 to 6 look like? So yeah, we talked about Kserve up here. Um, uh, Basically gonna route traffic to wherever the models are being served. Like it doesn't have to be one. You can have a bunch of different models being served. So yeah, and I guess where the level 7 would come in, it's just like I'd say like a proxy that gets injected to this layer 6 and sort of captures observability metrics. By layer 7, I mean like something like LLM. It captures some, I don't know, token usage metrics or other observability metrics, and then you can use it with things like OTel to export, um, yeah, to export those metrics somewhere else for like something like a cold storage for further analysis. And we'll see an example of this later on. All right. Uh, The okay, this is level 7. So I think yeah, I already talked a little bit about this, but level 7 is like the gateway, AI gateway. So you can track things like chargebacks, how many tokens are being used, some actual prompts. Like if you're deploying some agentic workflow, you can actually capture like the interaction itself for like further fine tuning or improving or fine tuning a model, so to speak. Um, there's also an emerging um, routing mechanism that's more not necessarily like a proxy routing, operational proxy routing, but more like algorithmic cognitive routing. So this is more like deploying a model. Instead of just deploying sort of like a proxy that's uh, capturing just standard traffic and payloads, etc. This kind of takes it a bit further and says, no, it's going to be a model that's actually going to be performing something, some additional intelligence for routing. Then that's like a cognitive routing. So maybe you have different model types, and this model might kind of route things differently to different models. All right. So just want to put that out there since it's something that's emerging. Um, okay. So now let's talk about a deployment. All right. So for this section, we want to cover like the next step. In a previous slide, we already covered like what the deployment looks like. Sorry, like the training phase. Like from gathering the data, from cold storage, how do you start to bring it to like a hotter tier and eventually to the cache? How do you train the data? And then how you evaluate it with things like LLM as a judge, etc. Once all that is in place, the next step is maybe like a continuous deployment event trigger that says something like, oh, our model is ready for the deployment phase. So what happens here is, so you might have like a stage 1, which is like a build and serve, a build a serving artifact that you might be doing. So we already covered the formats and things like that. So what this might do is start to containerize the artifact, and maybe Okay, sorry about that. So yeah, so it's gonna build the artifact. Maybe it's gonna perform some optimizations here, some additional optimizations, whatnot, or just package the final artifact somehow. So once this final artifact gets is ready, so a key tool here to use would be like Argo CD in Kubernetes, which is like a deployment, a continuous deployment tool. So you just say something like, okay, our model is ready to be deployed into like a staging environment. So the next step would be, okay, we've pre-provisioned some staging environment, maybe like a staging namespace or a staging cluster. So um, you'd deploy into this environment and just start bombarding this environment with some test data sets, so to speak. So you're going to be capturing like the metrics, capturing like the time to first token metric, like some behavioral metrics via like a light LLM, which is like the AI gateway we talked about earlier. Um, um, make sure like yeah. So you'll just be oh here okay so okay once you deploy this I should have said it goes to technical validation. So some of the things you do when technical validation we already covered, like the latency test, time to first token. Some just load testing is going to be an important one as well. Behavioral testing and evaluations, like LLM as a judge, that'll all happen here at this stage. Um, and any additional evaluation criteria that you may have to you may have defined earlier that you want to evaluate on. So let's say that this all passes and it's good to go. So the next step would be all right, or either we failed this test and why. Um, I mean, I think it's good to kind of have this mechanism in place, okay, and logging, etc. So it needs to be with implemented in best practices. Like, did it fail? Yes, no, and why? And maybe send that notification to wherever team or group needs to know about this, or agent to summarize some report of what happened. Uh, Without speculating too much, maybe even the agent implementing the fix. But that's a little speculative for now. But then if it passes, let's see, where's the pass? We also notify, right? We notify, okay, yeah, we need a review gate, human or agent. It passed. What do we do next? So maybe you merge it into like a production environment, and then you say, oh, um, Argo is gonna detect this change via like some polling mechanism that Argo has, and it's gonna say, oh, we're ready for deployment. So it's just gonna go ahead and deploy the rollout. So typical rollout here is gonna be like a canary rollout where it first rolls out like a 5% of the deployed models and starts capturing some data, some observability data, like network, etc., latencies, maybe even like hard prompts like a thumbs up, thumbs down, or things of this nature. So it's gonna capture all those metrics, and if things start to pass, it's gonna go ahead and roll out to the whole roll out the whole 100% of the traffic. Um, so I just outline here like Istio is gonna be the network traffic layer. Kserve handles the production rollout based on the strategy like we already discussed, Shout or Canary. Deployment at Light LLM is the model router as we discussed earlier, like the gateway, the proxy, and yeah, that's pretty much it. Now, what happens if you need to roll back? So that'd be something here. Something happens, you need to roll back. So since you're maintaining adequate records for your previous, uh, so Kserve should allow you to roll back easily, right? All right. So since we're maintaining adequate records and everything, so yeah, let's just so that's what a deployment environment may look like. Okay. All right. So there's an example of like a gateway. So you might like once all this ecosystem is in place, and you're actually capturing but bunch of you're like a commercial um what should I say, like a commercial model. You might or even not a commercial model. You're like even like in an enterprise, you might be deploying your model weights. So a useful thing to monitor here is light LLM. That's the level 7 layer. You might be able to monitor a bunch of things. So now we're going to start to get into like the observability aspect. So what you might things you might be monitoring are like the costs, token usage. You might start to this is where like agents, MCP, guardrails, things will come in. I don't know that we'll cover it. So yeah, just to give a quick walkthrough of what this is. So this is an AI gateway that was deployed for this model. So what's happening is we have this Qwen model deployed as kind of like the steps that we just specified. So we have an light LLM capturing all the metrics. We're intercepting sort of like the costs associated with this specific model. Um, and yeah, that's pretty much it for this one here. You can of course configure a bunch of different models. Even like if you deploy a LoRa adapter, you can also have that endpoint showcasing right here, which we'll probably see it later on. But you can also track things like agents, maybe that's going to be a common one. MCP servers, guardrails for things like, I don't know, maybe you need to, before providing some output back to like to a user, you probably need to sanitize it somewhat. So that'd be like example of a guardrail right here. Um, and yeah, yeah, this is more like how you organize, like maybe how you track your spending, so to speak. Yeah, and usage overall. So this is an example of like a LoRa adapter, what it may look like. So in this case, we took that Qwen model that we deployed. So that's the current Qwen model currently being deployed. We fine-tuned some adapter here. So this is what it's going to look like. So you may know it's just like some additional weights that are sort of injected here and there in the main Qwen frozen model, base model, 32 billion thinking. So once you deploy it, you need to configure some arguments and whatnot for in your VLLM runtime. And once you deploy the whole thing, in this case we fine-tuned like SRE agent, site reliability engineer, not an agent, like an adapter. Um, yeah. So that's you can also sort of query both models, so to speak. So you can deploy prompts to either the frozen weights model or your fine-tuned adapt model. And it's roughly going to be the same latency for both of them. And you can have a bunch of, that's why we call it like multi-LoRa hot swapping. Like you can also have, I don't know, like 10 more fine-tuned adaptations of this frozen weights model, and you can sort of hot swap them as well. Like, I don't know, let's say you have a finance one, but yeah, that's the main idea here, and that's just to give you an idea of what it'll look like. So at the end of the day, it's just some more weights that get injected um, into the frozen weights. Okay. So application integration. So this is where when we're gonna start to get into like the like agentic at MCP and tools in general. The topics we're gonna cover here. All right. So I guess the main so we've also seen in the same way that we're seeing like data versioning registries, maybe like container registries, data version registries. We have model registries, etc. We're also starting to see something called prompt registries. So I don't know if you've interacted with an AI model a bunch. Maybe there's some certain prompts that you run regularly. Uh, we didn't really cover much like things like temperature here or things like that, but maybe there's some. So temperature is just like a fine-tuning control regarding like whenever you deploy a model, how deterministic do you want the responses to be? Do you want it to always answer the same thing, or do you want it to allow a bit of exploration or randomness? But that's a different. But I guess if you find certain prompts to be particularly useful, especially as you start to like I don't know. Like let's say you have a research agent, right? Maybe you have a bunch of different prompts that allow you to summarize a report in a specific fashion, etc. So that's prompt governance. What prompt governance is all about. So it's kind of like storing the prompts and the model associated to the prompts that produce a specific for a specific workflow automation. Like I think we'll cover it in a future section. But that's basically what it is. Yeah, I guess, and you version your prompts and whatnot. But yeah, that's the reality. Okay, so so yeah, like the workspaces that we're seeing, I guess like since they're probably available earlier, but the explosion is from 2024 to today. So we have like these IDE copilots, which under the hood are like agents, and we'll see what an agent is later on. Some examples like Cursor, GitHub Copilot, Row Code, um, things like that. Open Code. These are yeah for like code development. You might have some other productivity tools like OpenClaw, etc. So I guess all of our traditional applications like Excel, Word, I don't know, video editing, picture editing, all of our productivity tools that we're using are now getting updated with these AI models. So so that's the main idea that we wanted to portray here, that everything's for AI embedded workspaces. Um, okay, I think we'll cover later on how this whole thing works. But in general, all of these are I just like to call them like agentic workflows. I think they're all under that category. So it's yeah, it's how your application interacts with some model. Yeah, I don't. Let's see. So let's cover tools, and MCP. So Model Context Protocol is um, is a protocol for like models to understand what tools are available to it. So by tools we mean maybe let's say you want to write like an AI agent that's for researching. So you sort of start to think, okay, what does a researcher do? It probably scans a bunch of literature and then summarizes it somehow. Then I don't know, perform some evaluation to see if that literature is complete or not. Some statistics. And if it's not complete, it has to go back into the loop of scanning more literature, maybe with different keywords or something like that. Then cycle through that iteration, and then maybe summarize results, etc. And once no more, something like that, right? So one of those tools that you might be using there is like a mining tool. It could be like a some mining actual literature, academic literature mining tool, or like a search tool. All of that is going to be that the communication is going to happen via MCP. So an LLM. So whoever's exposing a tool generally writes like pretty much like a REST API, but it's called MCP, so that your model knows how to interact with that specific tool. That's pretty much all it is. So whenever you create an agent, you'll give it a set of tools, let's say like a search tool, I don't know, some object store tool, or something like that. So pretty much to interact with, it's kind of like your API between your model and your like a database or something of this nature. So that's what MCP is pretty much. Yeah, this is where I wanted to get to. So this is like what an agentic execution loop looks like in pretty much in most of the scenarios. So this is taken from LangGraph documentation. LangGraph, as you might be aware, is pretty much a way to automate like a workflow. That's called like a workflow. So for example, you set up this workflow like the workflow would be these 4 blocks pretty much. So it's going to be plan, generate some to-do list, then execute those tasks. So it might use a tool to use this. And for the tool, let's say that it's going to do like a I don't know, like a booking hotels tool, or a search tool, or mining tool, something like that. So yeah, that would be the tool here, and then it's going to go back and say, did, are we satisfied with the results, right? But this is all kind of just you define the overall structure of this workflow, kind of like a regular block of code, but it's just like and then you give it to your model to kind of so you're just structuring this for your model. So just to give it to tell this one last time. So I use it. Say you have your PowerPoint presentation, like, or I'll just use the research example, right? So but agents in general is a subjective task, so it could be pretty much anything. So like for example, a site reliability agent to periodically check some metrics and logs from your system and just come back if there's any problem or things like that, or reason if there's some error, try to reason about it. And so let me just explain how this would work, right? So usually you would define these blocks, like the 4 blocks that you see here, and you call it like, in this case, your research agent. Let's give it research agent. So wherever the brain is, that means it's a model you're interacting with. It could be like a cloud model, like a Claude model, sorry, an Anthropic model, a OpenAI model, a Gemini model, things like that, etc. Or your own proprietary model, open weights model that you've deployed, or things like that. So that's what model is here, right? So you define these 4 blocks. I want you to first plan, then generate the list of things to do, then execute those to-dos. So here, if you put this into like a land graph, this is what a land graph is. It's like an execution workflow. So you would also have some tools available. These are generally going to be provided by the MCP server. You can read more about that in context of LangGraph, how that works. But it's essentially you'll have some tools available via like in your program, maybe like SQL to some database tool, some search as we discussed. So that's going to be the tools you have available to you. Maybe search the weather. Yeah, imagine the bunch of tools you can have available, and then just go back and say, are we satisfied? If not, rerun this again. Rerun this cycle until you're satisfied, or some limit is hit. Maybe you hit your token request limit and you don't want to overspend, so you could put that in there as well. So so let me just talk about this one last time. So for the planning phase, you send your request. I want you to research a topic on LLMs. So this guy's gonna be like, typically you're gonna have a reasoning agent. So it's gonna help you reason and generate like the tasks, the to-do tasks, right? So it's gonna generate 7 tasks, and then it's gonna delegate them to, again, to an agent. Okay, let's start executing task one. So your model here, you're querying your model again, and your model says, oh, I need to execute some search tool. Do I have a search tool? Yes, I do. So let's use that search tool and let's inject some keywords into that search tool and gather, I don't know, 20, 30 results, and some paragraphs or something. I don't know. So that'll come back to your model. Your model is gonna analyze the results and then maybe summarize or something here, synthesize those results and generate some results, right? And then it's gonna jump to the next block, and it's gonna again a second request. You're gonna say, okay, this is my current summary. What do you think? Have we covered everything? Are we missing something? Maybe your model here says nope, we're still missing something. So then it says your reasoning model says no, we're missing something, and this is what you're missing. So it'll go back to this, and then just execute this all over again until some condition is met. It'll give you back your result. So yeah, sorry for taking this long time, but that's just the way. This is an important topic, the agentic workflows. Probably going to be very important as well throughout the rest of the year and probably years to come. So, yeah, and you can, okay, let's just continue. All right, so something that's emerging as well, multi-agent collaboration and routing. So this is more along the lines we talked about cognitive routing. So this is sort of along those lines. So instead, yeah, it's having some additional reasoning or model intelligence handling all of this, coordinating like a bunch of agents, right? But yeah, like some examples of some agents would be like a retriever agent, retrieve relevant information, format it, like for yeah, uh, just yeah, math agent, so things like that that are specifically um, fine-tuned or optimized for their specific purposes. So that's something that we might see agentic meshes. It was just an example I wanted to give. So this is like me using row code, and I've deployed like a Qwen model and just how we interact with it. And in this case, we're giving it kubectl MCP, and it already it can also interact with our terminal to do things like I don't know, kubectl create config map, and so you give it the instructions in natural language. I know people that even just talk to these things without even typing, and it's doing they're bidding pretty much on their behalf. And yeah, so that's it's getting pretty advanced here. And yeah, let's see. I don't think we'll get more into it, but this is already kind of pretty like an advanced things. You can imagine like massive code migrations, troubleshooting. You can imagine a bunch of workflows that are currently happening. So like the agentic revolution type of thing. So that all happens via agents and MCP and just giving it access to your terminal. Of course, this is going to be important whenever you design things. Like maybe you just want to read access, right? Or are you going to give it write access as well? So I'm not sure if you want to give it write access to a production server or like a bank a bank server or something like that. But so you just have to be careful. Like how do you design these things? And you know you can always put some controls in like into your databases, like read only for this agent, things like that. This is an example of like a agentic execution. So in this case, we're using OPEAK. We captured all our data via like the Light LLM gateway, and we just wanted to see what this overall interaction looked like. So you might see things here like so this is actually part of observability we're starting to get into, but so this is a tool to trace a LangGraph execution loop. So the execution loop we described earlier, like a research, agent, but it can be really any agent. So maybe it starts to maybe you want to sort of run a trace on like, okay, what's taking the longest, and you want to start optimizing your agent for a specific uh, subjective task. So you can deploy things like LLM and in conjunction with OPEAK, and maybe perform some additional analysis. So in this case, the agent ran, and then there was some prompting here. There was tool calling, for example, that kubectl get pods was a MCP tool call that the agent decided to run by itself to see what pods were failing. So things like that, human interaction. That's kind of like this is a nice tool to use for like evaluating these uh, traces. I guess yeah, we kind of covered observability with that already, pretty much. But now the flywheel, which is very important. So if you recall, the first slide pretty much of this whole presentation was okay. Yeah, you're observing all of this, but it's also important on how do you update, how do you optimize, how do you improve your KPIs, right? So that's called the flywheel. Um, okay. So yeah. So I guess that's what we'll be covering here: observability and the flywheel. All right. So I guess here a few things that are important to track in this whole AI ops that we've covered thus far is infrastructure metrics, things like network, hardware, we have NVIDIA, CPU, memory, disk usage, etc. Although you're definitely so there are two sides of the house that you need to cover here. Like, what are the operational or infrastructure metrics that we want to capture? Um, Kubernetes, like, are processes healthy, etc. Like, what's our routing model routing look like? Yeah, like part of the infrastructure model, sorry, network routing, what does that look like? But there's also going to be a different type of things that you want to capture in observability. And that's what we were showing earlier, which is via light LLM, like your AI gateway proxy. So it's going to be more specifically tailored toward your model interaction or model monitoring, right? So we already covered things like cost, tokens, like uploaded tokens, downloaded tokens, token usage, I should say. Maybe those spans, like the ones we covered here earlier. Like what does an agentic span look like? Maybe you just want to capture a few of these so that you can sort of analyze and get like where are potential bottlenecks taking place, or maybe like the output. So that'd be for like optimization and analysis. Um, so yeah, that would happen via Light LLM. In the case of OPEAK, we captured all that data via Light LLM and then exported it to like we put it into you can also capture like early on we showed like a Grafana dashboard, so you can also cover like VLLM metrics, like the key value cache, how's that all behaving, right? Like the time to first token, all that you can also capture it from your runtime. And OTel allows you to sort of collect all that information, and then you can send it wherever you need to send it for like maybe yeah, maybe you want to run further analysis, so you can offload. So this would be an example, right? So you collect your observability data. You can export it somehow. You collect it via OTel. You can export it as an example to like a Kafka queue. You could consume that data and put it somewhere in cold storage or somewhere where you have more time to analyze larger uh, chunks of data. Something like with a tool like Presto or Spark. You might want to sort of perform some data engineering, maybe clean up a few things there, um, potentially visualize it or feed it back to like a training or fine tuning cycle. Yeah, of course, there's also an option to inject some potential alerts or whatnot. So some actionable items. Um, so something like to maintain reliability, site reliability engineering. All right. Um, okay, we don't need to cover this. This is just like specifying. So you can of course export this gathered data to a bunch of different endpoints. This is just an example, but there are many others. Um, it's probably not that mainstream, but sometimes you might have some model and you want to sort of analyze its internals. Like maybe what's the knowledge that's encoded into this specific model? Like for like treating the model as a black box. Maybe you want to just probe it and um, something like a model. We covered it earlier. So this is more like what should we call it? Like it's the name is forensics, so like model forensics. So maybe you want to kind of identify what model is encoded into this, what information is encoded into this model. Maybe there's some math in there, some physics, some I don't know. This is more like in the model forensics department, but there are some tools and mechanisms to sort of probe models and kind of identify what's in there. So, for example, a common use case would be what does an unquantized model look like? Now, once you quantize the model, what connections or what encodings were lost in there for like something like a quality model quality assurance? So, so you can there's a bunch of metrics you can look into, but the main idea I wanted to portray here is that there's also this thing called model forensics, and it kind of tries to it tries to look into the internals of models and uh, yeah. Now, for the retraining flywheel. Yeah, this is the last piece. So we already covered it pretty much in a previous section, but the idea here is to once you export all that, so if, let's say you want to improve your model somehow based on behavioral captures, um, you're gonna run through the pipeline where you prepare the model, which you need to like uh, which you want to feed into the fine tune for fine tuning your model or updating the weight somehow. So you might have a data engine that's gonna be like a standard data engineering data pre-processing step. What's the data that we want to update with? Um, how are we like what are going to be our evaluation benchmarks? And then you're just gonna do like upload your uh, upload your model weights. So that's something like what it may look like. For I should have said here maybe like yeah, like fine tuning your model. All right. And we already covered all of these concepts, except maybe Airflow, which is like a data engineering pipeline. All right, so we already covered this. Okay, I guess this is an example of the same dashboard, except here we're showing the actual GPU usage. So you see here like the GPU cache usage. So if this starts to spike, that's when you know, okay, that's yeah, you can essentially capture all those operational metrics and use them to your advantage, so to speak. Um, so there's some garbage collection running periodically. If you start to notice like your key value cache to increment without going down every garbage collection cycle, that means that there's some memory leak somewhere in there, and you need to kind of address it. There's the prefix cache savings that we discussed earlier. So if you configure prefix caching, it's very useful uh, for inference time serving quality of service. And Yeah, tokens per second processed, both for up and generation, and yeah, prefix cache hit. So there are a bunch of these are all metrics that are readily available, and your these are for VLLM engine, and you can track to kind of optimize or identify potential leaks or something. So that's it for this presentation.